Welcome to this video lecture on compressible flow. This is an introductory lecture to compressible flow. We're going to talk about some review of thermodynamics as well as some things that make compressible flow special when compared to incompressible flow. So take a look at your screen. We have a really neat picture here of two T-38 trainers flying. This is a real photograph. It's been colorized a bit, but it's a real photograph. So you have two T-38 supersonic trainers that are going faster than the speed of sound here, and the image is a schlieren type of image. Schlieren, let me write this down here. Looks like this. Schlieren photography. Schlieren photography, what it does is it images where you have gradients in the air density. So large gradients in the air density. So everywhere you see a line, it doesn't show up that well here. Let me see if I can get a different color. So everywhere you see a line like right in here, this is where the density of the air is changing very rapidly. And the reason you're seeing these rapid changes in the air density are because you're getting shock waves that are forming on the surface of the aircraft, and then they're propagating out and interacting with one another and such. Shock waves, as we'll learn about in another lecture, are where you get very abrupt changes in the air density, the air temperature, the pressure, and the velocity. And they only occur in supersonic flows. So that's a topic we'll talk about later. So that's one big difference between compressible flow and incompressible flow, is that with a compressible flow you can get these kinds of shock waves that occur. And we'll talk about later why they occur and how we would analyze them. And so what Schlieren photography does is it basically makes use of those density gradients, or it images those density gradients in a special way. We don't have time to really talk about it in this course, but you might want to take a look at it on the web. It's a neat technique. There's a similar kind of technique called shadow graph photography that also relies on gradients in the air density. They're different techniques, but they produce similar kinds of images. But anyway, this was a real picture taken up in the atmosphere of these aircraft. It was a real challenge, apparently, to get this taken, but it's pretty neat. All right, so let's go ahead and get into some of the material. First of all, we're going to do a little bit of review of thermodynamics. That thermo course you took before you took this course. Turns out it's pretty useful for fluid mechanics, especially for compressible flow. So we need to review some of that thermodynamics. We're going to use a lot of it. First of all, let's talk about some of the basic definitions. Little u will be the specific internal energy. We have specific enthalpy here, which is just the specific internal energy plus the pressure divided by the density. The specific heat at constant volume, specific heat at constant pressure. The specific heat ratio you'll see a lot in our analysis here. So that's the C sub P over C sub V. And a number that's worth remembering is the specific heat ratio for air, equaling 1.4. So that's a number we'll use frequently, so try to remember that one. Similarly, the gas constant for air we'll use quite often. And in metric units, it's 287 joules per kilogram Kelvin, so just remember that one. It's not the universal gas constant, but it's the gas constant for air. Some definitions that we'll use quite a bit. We'll talk about adiabatic flow. Often that's where you have no heat transfer occurring. Reversible flows. These are flows where the system and surroundings can be returned exactly to their original conditions. When you have viscous effects, then those flows are irreversible. So we'll talk about situations where we can assume reversible flow, where the viscous effects are negligible, and then of course in real life situations there's always some irreversibility. Those shock waves I showed in the picture at the very beginning of the lecture, those are irreversible processes. So we'll talk about that when we talk about shock waves. Isentropic flow, this is where the entropy remains constant in a flow. And of course, if you remember back to your thermodynamics, reversible and adiabatic flows are isentropic. So if you have a reversible and adiabatic flow, then that means it'll be isentropic. And we'll use that as a model pretty frequently in our analysis. And I guess that was that next bullet point. And then lastly, we'll use TS diagrams pretty frequently for compressible flows. The ones that we deal with in this course are really straightforward. most of the flows we'll work with are isentropic flows. So the TS diagrams will just be paths along the vertical direction where S, the entropy, is on the horizontal axis. So anyway, these are all review topics from your thermodynamics course. You just need to be refamiliarized with what the terms mean and such. We'll deal primarily with air in our analysis of compressible flows. So we'll use the ideal gas relations. So we have the ideal gas law. So P is pressure, rho is density, R is the gas constant, T is the temperature. Just one thing to keep in mind is that you need to be using the absolute pressure and absolute temperature for the ideal gas law. Also for an ideal gas, the change in the specific internal energy for an ideal gas is equal to the integral of the specific heat at constant volume times the small change in temperature dt integrated from the initial and final temperatures. And just keep in mind that the specific heat is a function of temperature in general for an ideal gas. Similarly, change in specific enthalpy for an ideal gas is the integral of Cp dt, where Cp is also a function of temperature in general. You can show that Cp is equal to Cv plus R. Again, this is all review from thermodynamics. And then just some more relations involving Cp and Cv, the gas constant, and the specific heat ratio. And then one that we'll use often is this expression relating changes in entropy for, again, an ideal gas to the specific heat ratio, temperature, density, and a gas constant. So you can see those relations. Now, I said that the specific heat ratios are in general a function of temperature, and I show that over here for air in this plot. So here there's specific heats. There's the C sub P and C sub V as a function of temperature given in Kelvin. And so you can see that in general they are functions of temperature. But often we deal with smaller ranges of temperature changes. So let's say if we were dealing with a temperature change between 200 Kelvin and 400 Kelvin. If you look at, let's say, C sub P here, it does vary between those temperatures, but not by a whole lot. Okay, so over a few hundred Kelvin temperature change, it's not unreasonable to assume that the C sub P and C sub V are constants. It's an approximation for sure, but it's a reasonable one. And so we often make that assumption that we're dealing with constant specific heats, and then when we deal with an ideal gas with constant specific heats, we call that a perfect gas. So that's this expression down here. Perfect gases are ideal gases with constant specific heats. So this expression up here where we had to integrate the CV for an ideal gas, if it's a perfect gas, the CV just comes outside the integral, and it's very simple, and you get the expression down at the bottom of the page. Similarly, you can do the same thing for the specific enthalpy, and then also the expression we had for the change in entropy, specific entropy, you can actually integrate that one and you get these expressions here. So those are perfect gas relations. Again, that's an ideal gas with a constant specific heat or constant specific heats. Perfectly reasonable assumption when you're dealing with small temperature changes. Now, if we were dealing with an isentropic process involving a perfect gas, then the S2 minus S1 would be 0 in that expression. And so then you can now relate temperatures and densities, or temperatures and pressures, or combining the two, you could relate pressure and density. And that's what's given here. So we'll make use of these relations often as well. So isentropic process involving a perfect gas. You can see how the temperature and density are related through the specific heat ratio, pressure and temperature relation, pressure and density relation. So again, everything that I've presented so far should all be review for you. You just have to refresh your memory from your thermodynamics course. Okay. One last thing I'll do before I make a few other comments is we're going to make use of the first law of thermodynamics quite frequently in this portion of the course. And so let me review that, and specifically with some of the assumptions we'll be making. So the first law for a steady flow, we're only going to consider steady flows, of a gas. Okay, so when we deal with compressible flows, if you remember back early in the course, we talked about how liquids can generally be assumed to be incompressible. That's a very good model. And indeed, that's the case. Liquids typically assume those are incompressible. Gases, if they move at a slow enough speed, and that rule of thumb is less than 1/3 the speed of sound in that gas, then they're often modeled as being incompressible. It's not a bad approximation. When they're going faster than that 1/3 the speed of sound, then the compressibility effects start to become important. It's very hard to get faster than 1/3 the speed of sound in a liquid. It's a very challenging thing to do. So we just always treat liquids as being incompressible. Gases, however, it's not hard to get faster than 1/3 the speed of sound in a gas. Planes fly at high enough speeds where compressibility effects are common. You can have even just like building shop air coming out of a nozzle that can reach speeds where compressibility effects are important. So when we talk about compressible flows, often that field is called gas dynamics because it's mostly gases that you have to worry about compressibility effects for. So we're only going to consider gases in this section of the course. And by the way, when you deal with gases, if you think about the Bernoulli's equation, you had that pressure term and a kinetic energy term and a potential energy term. That potential energy term is very, very small in comparison to the other two terms when you deal with gases because the densities are so low. And so we'll make use of that assumption here since we're dealing only with gases. So that'll show up in just a moment. We'll say we're dealing with one inlet and one outlet. We're just restricting ourselves to simple one-dimensional flows, really. And then uniform inlet and outlet properties. This again goes to kind of one-dimensional flow. So here's the first law. We've covered this actually when we reviewed pipe flows at the very beginning of pipe flows and deriving the extended Bernoulli equation. We started with this equation. The first term is the time rate of change of total energy within our control volume. That's 0 because we're dealing with steady flows. Then we have this term. This is the term in these brackets here is the total specific enthalpy. So you've got specific enthalpy here, the kinetic energy term. Here's the potential energy term, but we said we were going to neglect this one because we're dealing just with gases. So that'll go away. Here's our mass flow rate term. And then this is the rate of heat transfer into the control volume and the rate of work done on the control volume due to other effects, things other than pressure. And typically, we will not worry about other types of work. We're not going to worry about turbo machinery or electrical work or anything like that in these flows. It's only pressure work, so that last term will actually go to 0. Since we're dealing with one inlet and one outlet, the mass flow rate at the inlet and outlet will be the same because it's a steady flow. And then if we substitute that in with these approximations I said before, our first law expression just ends up becoming this expression. The little q and the little w are just the heat transfer per unit mass flow rate and the rate of work per unit mass flow rate. And then if we assume that we're dealing with an adiabatic flow, such that there's no heat transfer and no work other than pressure work, such that the little w is 0, then we end up with this expression. Or, since this is just the change between the inlet and outlet of this kind of total enthalpy term is equal to 0, or the total specific enthalpy remains a constant. This expression is a very important one in compressible flows. It's incompressible, not incompressible, but for compressible flows. So that's one that we're going to refer to quite often. And since we're dealing with ideal gases and often with constant specific heats, namely a perfect gas, we can simplify the change in the specific enthalpy as Cp times delta T, and so we'll get this expression for a perfect gas. So the final expression there in yellow, this one at the very bottom, is just the culmination of all of these assumptions operating on the first law. Okay. The nice thing about this is it gives us a way to relate temperature and velocity. It's kind of like Bernoulli's equation, really. It's just, Bernoulli's equation dealt with pressure and velocity for a gas. Well, this is like Bernoulli's equation, but for compressible flow. And it relates temperatures and velocities together. So that'll be a very fundamental relationship for our analyses. But to get to that point, we had to make a number of assumptions, right? One inlet, one outlet, steady flow. We're dealing with no heat transfer, only pressure work, and a perfect gas. Okay, so a lot of assumptions into that one. So again, this kind of simplification here, you've seen something like this before in thermo, and you actually did something quite like it when we derived the extended Bernoulli equation for pipe flows. So it shouldn't be unfamiliar to you. Okay, let me just, so now that's our quick review of thermodynamics. Hopefully it may feel a little rusty to you, but hopefully it's not completely unfamiliar. Let me spend a little bit of time now talking about some of the differences between compressible flows and incompressible flows. So first of all, with a compressible flow, it takes time for information to propagate from one point to another. And we're going to talk about this in the next video lecture, but there's a speed of sound. The speed of sound is the speed at which a very small pressure disturbance propagates into the flow. So with an incompressible flow, what you'd find is that the speed of sound is infinite. That if you make a perturbation somewhere in the flow, it's immediately felt everywhere instantaneously for a truly incompressible flow. But when the flow has some compressibility to it, it takes time for that disturbance to propagate. So if you make a change somewhere, it takes time for that disturbance to be felt elsewhere. And you can start to run into some really interesting situations where you start to move as fast as the disturbance propagates. So basically, you start to move as fast as the speed of sound, or maybe even faster than the speed of sound. In those kinds of situations, you get the development of these kinds of shock waves. So you'll see situations, if you're going faster than the speed of sound, you can get a shock wave that forms. You can also get what's known as choked flow when you discharge vessels. So a choked flow is if you pressurize a container, let's say a big gas container, and you discharge it to the atmosphere. A choked flow is where even if you change the back pressure, the pressure that the tank is discharging into, you can't make the flow speed up anymore. But I guess let me sketch out what I'm talking about. So let's say we have a tank, and I have some pressure in here in the tank. I'll call it P naught. That's the pressure inside the tank. It's at stagnation conditions, right? It's not moving around. And then we have the pressure out here, which we call the back pressure. That's the pressure it's discharging into. So if we have this pressurized tank and this back pressure, of course, if we decrease the back pressure a little bit, then we get a pressure gradient and we push some fluid out through that, that nozzle or hole or what have you. But what you'll find for compressible flows is, as I continue to decrease the back pressure, the flow here will increase. But then there'll come a point where even if I decrease this back pressure further and further, I won't get any more flow rate out of that hole. It becomes what we call choked. There's a maximum mass flow rate that you can get by only varying the back pressure. So that's another interesting effect of compressibility, but it's due to the finite speed of sound in compressible flows because the pressure waves can't propagate upstream into this tank. And that's something we'll talk about in another video lecture. So you get these kind of interesting effects that occur because of the finite speed of sound. Now, another thing that I want to mention is, in our review of thermodynamics, I talked about, let me see here, isentropic flows. I said that we'll deal with isentropic flows frequently in this course. I'm going to talk about that a little bit later, but let me just give you a preview of it. If we have flow through a pipe, let's say, we know in real life from our discussion of boundary layers that you get the formation of a boundary layer, right, that occurs in the pipe. And there are, of course, viscous effects in that boundary layer. That's where all the viscous effects are concentrated. But in the core, the flow remains inviscid. So if we have short lengths of pipe, they have to be relatively short, or like a nozzle kind of shape like this, where we get the development of the boundary layer as it goes through there. The boundary layers are pretty thin, so most of the flow field is actually inviscid, right? So it's mostly inviscid, and because if we're dealing with short lengths, often there's not a whole lot of heat transfer that's occurring to the environment or to the surroundings, right? Between the flow and the surroundings, the amount of surface area in these kind of short lengths of pipes and short nozzles, maybe they're insulated as well, there's very little heat transfer that occurs. So if we assume that there's no heat transfer, that means it's adiabatic. And if we assume that we only deal with the inviscid core, which is most of the flow, the boundary layers are thin, so really most of the flow is inviscid core. So if we have an inviscid flow, that's a reversible flow because the viscous effects cause irreversibility. But if we don't have those, then we have a reversible flow. So in these kinds of situations, we have adiabatic and reversible flow, which means it's often treated as an isentropic flow. It's an engineering approximation that works pretty well, in fact. So we'll come back to that in a different video lecture. All right, I think that's all I need to say about thermodynamics review, and I gave you a little idea of some differences between incompressible flow and compressible flow, a couple of interesting effects that we see with compressible flows. And we'll address these things in more detail as we get to them in upcoming lectures. So in the next lecture, what we'll do is we'll talk about the speed of sound and an interesting phenomenon known as the Mach cone. So we'll do that in the next lecture.